Hello, I am Advait Mane, presenting our trajectory optimization formulation with smooth analytical derivatives for track leg and wheel leg ground robots. Wheels, tracks, and legs are all useful means of locomotion for UGVs. Each has its advantages. Wheels are efficient on flat terrain. Tracks provide more traction than wheels and are good for moderately rough terrain, and legs can traverse larger obstacles and maneuver through cluttered environments. UGVs such as PackBot and Chaos combine tracks and legs, and Robosimian, Centauro, and Animal combine wheels and legs to achieve a practical compromise. As UGV morphologies become more complex and larger obstacles are encountered, more sophisticated motion planning is required. Our formulation can be used to plan motions for such morphologies. We derived the dynamics for a circular wheel on a ramp and an elliptical track. We used Lagrange multipliers to enforce the locomotion constraints and assumed no slip. We combined these with multi-body chains and applied Lagrange's equations to obtain closed-form dynamic models of wheel leg and track leg UGVs. For motion planning, we used direct collocation implemented in MATLAB. Z represents the state and U represents the actuator torque. We defined an objective, for instance, the integral of the actuator torque, subject to dynamic and algebraic constraints. The objective and constraints are closed-form expressions with smooth derivatives, which speeds up the computation. We then solved the problem as a nonlinear program using IPOpt, and the computation time for all our optimizations was less than 40 seconds. We now present the results for several tracked and wheeled systems. Here we see a track approximated as an ellipse circulating around the body. We observe dynamic coupling as the track acceleration causes body counter-rotation. Next, we have a tracked double pendulum performing dynamic balancing. We also implemented a tracked bicycle. The base is constrained to remain horizontal, and the tracks continuously adjust to achieve this. These results show the variety of behaviors that can be achieved with our formulation. This example contains uneven terrain represented by two piecewise linear terrain segments. There are three contact modes. In the first contact mode, both wheels roll on the flat segment. Then there is one wheel on each segment, and finally both wheels are on the ramp segment. This result shows that our formulation works for multiple contact modes on uneven terrain. Finally, we have an articulated UGV on uneven terrain. The task is to use the front wheels to traverse the step obstacle. This result shows that our formulation can lift the wheels to change contact modes and traverse an obstacle. In conclusion, we developed a trajectory optimization framework for wheel leg and track leg UGVs with computation times under 40 seconds. And we demonstrated this framework on multiple UGVs completing an assortment of locomotion tasks. Thank you for your attention.